I'm Sam.
And I'm Paul.
And we're trying to do an extra credit math video for our math class.
We were supposed to do a catapult, a teeter-totter.
To measure distance equals rate times time, but
it didn't work. Yeah, it didn't work at all.
So what happened?
We got wet.
Our original plan was to throw water bags of different measured weights using a catapult we built ourselves. We wanted to measure the effect of different weights on how far they went. Unfortunately, we ended up with a seesaw instead of a catapult, and it didn't throw things very far.
Alright, let's go. 1, 2, 3. Oh. Alright, we're not going to do that again. Dude, that didn't work at all.
Yeah, I know. But since we made a really nice lever, my dad remembers an experiment in high school that he did with the lever function, and he did challenge us to discover it.
That sounds good. Because I don't want to get wet again.
A small weight can balance a larger weight if they are put at the right distances from the center of the lever. We're going to track weight 1 and distance 1 against weight 2 and distance 2 that balance. Then we'll see if we can do the math. Maybe a graph could help us turn our test data into a real tool. The lever has been marked with lines at 1 foot intervals for measuring. Paul will start by balancing a 20-pound weight on a line 1 foot from the center of the seesaw. I will try to balance it using a 5-pound weight and measure the distance from the center, and we will start to build our data. After our data collection efforts, we attempted an ambitious test with human subjects. Despite the fact that we did not have FDA approval, the results were inconclusive, due to the inherently flawed nature of the 14-year-old male of the species, basically us.
Alright, we have the data here. I think we should graph it because there's the weight and the distance always equals the same for both things, and then it changes over here. So let's graph the stuff that changes. Alright, we're gonna make this the distance, and we're gonna make this the second weight. 5.
Skip 2. 1, 2.
10.
There you go.
15. 20. 25.
30.
Alright, so we know the weight is always 20. And then the distance either equals 1 or 3. So let's first graph what the distance for 1 is. We have the weight number 2 is 5, and the distance is 3.9. So 3.9 is 5. Then we have 2.2 and 10. Alright, now this is pretty close to a straight line, so we're going to get something straight and make a line.
No, 15, 4.1. 15.
Alright, now we have our both lines. So we found a formula online, but it didn't really work because we found out that there's more than one formula for levers. So we were kind of fooling around, and we found the other formula. Is you times the first weight by the first distance. And then what you would do, it equals 5 times
Second weight times
3.
the second distance.
Yeah, the second weight times the second distance. So 20 equals 20. So that works for the first one. Now if we round 2.2 to the lowest one, that equals 2. 2 times 10 equals 20. That works again.
And we found this out all our own.
Yeah, we found it out all on our own.
What am I supposed to do? Okay, so 20 times 3 is 60, and 30 times 1.9, which is rounded up to 2, which is 60. 20 times 3 again is equal to 60, and 22.5 times 2.65 should be 60.
Should be close enough.
We'll do the math.
5, 2, 6, 9, 5, 1, 2, 3, 4. Oh.
So you're looking for 60. What'd you get?
59.625555555555.
We got the graph. We got the equation. I think we're done, don't you? I call it the Paul and Sam equation.
I call it the Founds equation.
Why don't you call it done with this video and say thank you very much?
Yeah, I agree with that.